So, we will see one more example of importance sampling in the Monte Carlo technique that we have learned, and this time we are going to focus on statistical mechanics or statistical physics, and we will look at phase transitions, and we leave out critical phenomena because that becomes too technical from the physics perspective. So, we just talk about phase transitions and how Monte Carlo aids in seeing or demonstrating a phase transition. So, as a prototype system, we will take an Ising model and we will describe what an Ising model is. And so, phase transitions are really important things in condensed matter physics or statistical physics, where the system changes from one phase to another as a function of the driving parameter, and that driving parameter could be anything which could be related to the the parameters of the Hamiltonian, or it could be thermal effects, which is temperature, or it could be other things such as a bias voltage and things like that. So, these study of phase transitions is always important and interesting because the system changes from one phase to another. So, let us take an example as the Ising model. So, what is an Ising model? So, it is a model of a magnet, or it shows magnetism, and that also has a phase transition. So, it mainly shows a magnetic phase transition, and that is what is being used for. The essential idea, the premise behind it is that which is also true for many other magnetic models such as Heisenberg model, etc., that the bulk magnetism of any substance or any material, it results from the contribution of the magnetic dipole moments of many atomic spins coming from the constituents atoms or ions for that particular element or that particular material. So, we are going to talk about magnetism, and magnetism is coming from the magnetic dipole moments of the atomic spins. And this Ising model postulates a lattice, and in principle this lattice could be of any geometry, it could be in any dimension, it could be in 1 dimension, 2 dimension, 3 dimension and so on. And the geometry could be a linear chain in 1 dimension, or a square lattice in 2 dimension, or a cubic lattice in 3 dimension. You can have a simple cubic lattice, or you can have a FCC, face centered cubic lattice, or a body centered cubic lattice. In a 2 dimension, one can have a honeycomb lattice, or one can have a other more complicated lattices such as Kagome, etc., and so on. And with a magnetic dipole or a spin located at each of these lattice sites. Okay. So, suppose we are talking about a 2-dimensional square lattice, which is easy for us to demonstrate. So, these are the lattice sites, the corners of where there is vertical and the horizontal lines they intersect. So, these are the lattice points, and here let us draw it with a different color. There are spins which are pointing like will in principle in any direction, but for Ising model we will talk about only spins pointing up or down. You have drawn a little out of the axis because just to show you the direction, but these are perfectly either pointing up or pointing down. This is like a z component of any spin half object, and so everywhere there is a spin of this kind, and we want to see whether this has a finite magnetism. And for that one has to postulate a model or a model Hamiltonian, and for the Ising model, the model Hamiltonian looks like here. Just let us come to this in a while. So, these spins in this model are represented by scalar variables which we call as SI, which can assume only two values, namely +1 and -1. Okay. So, they cannot take any other value. So, plus will correspond to say up, and minus will correspond to down, but that is just a convention. You can take your own convention to be just the opposite of this convention. So, the interaction between the spins, and that being the only term in the Hamiltonian, is between the nearest neighbor spins, these spin variables Si. So, it is Si into Sj is the spin variable. So, there is a sum over, let me write it, Ij, not put this sum over. So, these are sum over i's and these are. So, when we write like this, these are nearest neighbors. Okay. And B is an external magnetic field. And this negative sign is simply conventional, and J can have either a plus sign or minus sign. If it is a plus sign, then that would facilitate, or rather that would promote that all the spins pointing in the same direction. So, either you have plus 1 into plus 1, which will give you a plus 1, or you can have a minus 1 into plus a minus 1, which will again give you a plus 1, so that the energy is minimized by the spins pointing in the same direction. So, if it is between two neighboring sides, that is true for all the neighboring sides in the lattice. So, the essentially all the spins would be pointing up, and one would have a ferromagnetism in this particular situation. If J is negative, then it is energetically more favorable to have these neighboring spins align in the opposite direction, that is one being plus, the other being minus, in which case the product will be minus, and hence this minus will multiply with this minus to give me a sort of plus sign, but then J being negative, that will minimize the energy. So, that corresponds to an antiferromagnet, where the neighboring spins are pointing in the opposite direction. And what one does, or what one if one has gone through this statistical mechanics at the Patria level, or even at the Rife level, one knows that the thing to calculate is what is called as a partition function, and usually we talk about the canonical partition function, which means that this system of n Ising spins on a lattice is connected to a bath of temperature T, and this is given by, so the magnetization is given by the expectation value of the spins at a site I, and this is written as 1 over beta del log z del beta I, where z is, as said, is the partition function. It could be the canonical or the grand canonical partition function, and it is the derivative is taken with respect to the magnetic field at the site I, and this would determine that whether the system is in a paramagnetic state when m would be equal to 0, that is, there is no net magnetization of the system. And for ferromagnetic system, or for magnetic system, say for example, in general, the value of m is not equal to 0. Okay. So, this would tell us that whether we have a magnetic system or magnetized system or a non-magnetic system. Of course, if B is large, then you always have all the spins pointing in the same direction as this external field. But most of the time we want to talk about the spontaneous magnetization, that is the magnetization that one can have without this B term. So, that the driving, or rather the competition, is between J and kT, where kT is the thermal energy which will try to randomize all the magnetic moments or the spins, and that will be done by the kT, which is the thermal energy, and J is the magnetic term which will try to align them, given that J is positive and with a negative sign at the front. So, we will have a magnetic system. Okay. So, most of the time we are interested in these spontaneous magnetization without the second term in the Hamiltonian, but it could be there, and it poses no problem, because it is a one body problem or one body term, and there is no problem in diagonalizing the Hamiltonian even with this term being there. So, we essentially try to compute m. Okay. And this m is the magnetization, as we have said, and this, let us say, the average magnetization and things like that. Okay. So, where is Monte Carlo coming into the picture, and how do we get these Monte Carlo associated with this problem? So, usual goal in Monte Carlo simulation is to compute the expectation value of an observable that we have seen. The expected value or the expectation value or just the expectation are various terms that are coined for that. As you go through literature, they have different nomenclature. Now, this particular expectation value of an observable could be the magnetization as we commonly know it, that this magnetization is an indicator of phase transition, because if the magnetization vanishes, the system is said to be in a paramagnetic state, and if it is non-zero, then it is a magnetized state or a magnetic state. And this is exactly what we have just discussed. And then we can have a phase transition as a function of the driving parameter from a paramagnet to a ferromagnet. Okay. There is no at here. Because we shall talk about the systems in thermal equilibrium, okay, because temperature, any experiment that you can think of is not done at 0 temperature, it is done at a finite temperature. So, temperature will definitely play a role, or rather this ratio, as we have just said, that this ratio will play a role, because if J is very large compared to kT, then we have a magnetic system, as I said, could be ferromagnetic, and if in the other limit, if J is much smaller than kT, then we have a paramagnetic system with no magnetic properties. Okay. So, this ratio is very important in determining that whether the system has a ferromagnetic property or a paramagnetic property and things like that. So, just what we have written in the last page about this expectation value of SI, S being the spin variable at a given site I. Let us just talk about Q, any sort of quantity for which we want to calculate the correlation function or these expectation value. And then what we have to do is that we have to take these Qi and which is exponential minus beta Ei being the energy of the system, and I is not, so there is a bit of a sort of notational issue. This I is not a site index that we have said earlier. So, what we can do is that we can change this, if you like, to Mn and write this as Sm Sn, and maybe this as say M, and then we can write this as Sm. Okay. Anyway, that is just so we know that these M and N are actually these site indices of lattice, could be in 3 dimension or 2 dimension, as we have said, or in any dimension, and any lattice geometry. And so, this I rather would be the number of states that we are going to sample, and as we have said that these states are generated at random from certain distribution, and so this is I is 1 to M, where M denotes the number of states, or I mean basically M is the size of the sample, or I mean sample means it is not the sample, it is not the material, but it is the sample of the states, or rather the number of states that we are going to consider from a arbitrary probability distribution. So, we have learnt how to do these summations or integrals by using the Monte Carlo. So, the Monte Carlo crude or the simple, as we have said. So, crude and simple, if the word crude seems a little crude, then you can use the word simple. The simple Monte Carlo estimate of Q would be given by this, where Qm. So, this is equal to Q is replaced by, or the expectation of Q is replaced by Qm, which is equal to a Qi Pi and an exponential minus beta Ei. Okay. And divided by, all these are sum over i's which are not appearing here, and pi and exponential minus beta ei. So, qm becomes more and more accurate if m goes to infinity, which means the sample of states that we are considering goes to very large values. But then as you know that we have a definite computational power and we cannot go to any number of states to sample in a physical computer. But this is true that if m goes to a very large value, that is going to limit in the limit tending to infinity, your qm will give you the accurate estimate of this expectation value of q. And if you are wondering what q is, it could be anything for a given thermodynamic system. In this particular case, we are having magnetization in our mind. So, now the question is how does one choose the probability distribution pi? Okay. And the simplest choice is of course to pick all states with equal probability, okay, with no a priori assignment of probability. So, completely unbiased. So, it is an uniform distribution. So, this uniform distribution we have seen that they are not very helpful, because there are too many of them, one, and secondly you do not know how to distinguish sort of the more important states from the not so important ones. And particularly the problem is more important, as we are also going to come later, is that since we are talking about low temperature, that is we are actually looking for the system to order as we tune this j by kT, which means that j is larger than kT. So, we are in a limit of smaller temperature. It is only the system only spends more time, or rather mostly be found in a few states among this large number of or a plethora of states that we are having. So, it is just only going to be residing in these few states which are only most important, and the rest are not important and not contributing to this sum. So, that tells you that if you take a random distribution, which means a equal distribution, uniform distribution with equal probability, then that pi can be taken to be as 1, and then this qm reduces to a particularly simple form, which is qm equal to again this sum over I and exponential minus beta ei. So, just to remind you every time that beta equal to 1 over kT, that is the convention that is used. Might have written it somewhere, but if not, then I will write it, should have written it here. So, beta is equal to 1 over kT, where k is called as the Boltzmann constant, and T is the temperature in absolute scale. Okay. All right. So, we are with a uniform distribution, we have an expression for qm which looks simple, but of course, we know that from our experience that this must be a poor choice, because you are giving equal weight to all states, whereas all states are not really involved into this sum. We have seen a particular problem that the function has a value which peaks around a certain value. So, if you take a uniform distribution, you are really you have equal probability of choosing points from the tail, which does not contribute much to the value of the integral. That is the one that we have seen in the last discussion. So, we know that these uniform distribution is rather a poor choice, and perhaps something better should be done. So, let us just look at these the details of these simulation and implementation of the Monte Carlo. So, in an Ising model, let us take a 3D cubic system, simple cubic system of 10 L equal to 10. So, 10 cross 10 cross 10 Ising spins, which are thousands spins, and each spin has 2 states. Okay. So, if you have 2 spins, one can have states which are like up up, or which can have up down, or which can have down up, or which can have down down. So, these are 4 states which is equal to 2 to the power 2, because we have 2 spins, we have 2 to the power 2 when you have n spins. So, you have a 2 to the power n. Now, since we have 1000 spins 10 into 10 into 10, which are arranged on a simple cubic lattice, you will have 2 to the power 1000 states, and that is a very, very large number, and that is a number which is close to 10 to the power 300 states. So, if you really have to sample 10 to the power 300 states, that is no physical computer available even as today would be able to sample them, and neither there is a need to do that. So, at a typical good computer would do it up to something like 10 to the power 10 states. So, what happens is that you are leaving out to 10 to the power 290 states from the 10 to the power 300 states. So, the sum that you are trying to calculate, which appears here in this expression for QM, is dominated by only a small number of states. The other states actually contribute very little, but even those small number of states you are going to miss, because you are only you are going to miss a 1 in 10 to the power 290 states, and this is going to be a very bad approximation, because the ones that are dominantly contributing to the integral are being missed, and these are not helpful at all. So, a QM will eventually give a very bad estimate of Q, okay? And that is the reason that the importance sampling comes to the rescue. Okay? So, we are going to now use importance sampling and actually sample states which are accessible or achievable by a physical computer can sample, and we will have to only demarcate those states, and we have to have a rationale behind that. So, we have learnt importance sampling, we just want to recapitulate it in this particular situation. So, we know that on the other hand, if we have some ways of knowing which states could make important contributions to the sum above, we could pick them into our sample of m states and ignore all others. This is done by the importance sampling. Okay. So, our strategy would be to instead of picking up m states randomly from a uniform distribution, we want that every state of the system so every state of the system is not as likely as any other state, rather we pick them from a probability given by this 1 over z and exponential minus beta I. So, this is like sum over I exponential minus beta I. So, this is the probability that is going to be used, not the probability 1 which corresponds to a uniform distribution. You remember that we have used Gaussian or a normal probability distribution with some mean and variance for solving an integral that appeared in the last discussion. In this particular case, that Gaussian distribution is replaced by this one, this distribution, this pi, where z is as you have learned that z is called as the partition function of the system, which is sum over all states, all configurations, and exponential minus beta ei. So, the Monte Carlo estimator takes a particularly simple form where Qm equal to 1 over m and sum over Qi, and because all these Boltzmann factors that have completely cancelled each other, and you are left with only a Qi, and so this particular formalism, or rather choice of this probability distribution entirely depends upon the problem, and one has to use really common sense and looking at the integrand or the function that needs to be integrated and carefully, and then decide on the probability distribution for doing the importance sampling. So, this is the importance weight that we have learned in order to do this problem. Okay. So, Qm really takes a form which is 1 over m and sum over I Qi, and we have cancellation of these Boltzmann factors that are there. Now, the question is that how exactly do we pick our states? Okay. It is not only about the probability distribution, but for the reason that you will just see in a short while. Um, so, we have to make a strategy for picking up the important states, and as I said that at small temperature not all states are equally likely to contribute to the integral, and there are a certain number of states that are important, and one has to really know the technique in order to do that. So, it is really not a simple task, and it is done by a technique which is called as a Markov process. So, all Monte Carlo techniques really rely on this Markov processes as a generating engine for the set of states that will be used for computation of the expectation value. Okay. So, what is the Markov process? The Markov process is a mechanism which a new state nu starting from an old state mu with a transition probability p going from mu to nu. Okay. So, you have a state mu and you want to go to a state nu, and there is certain probability for going towards that. This is done by the Metropolis algorithm, we will see that in a while, but there is a probability, and then from again from nu one can go to another one called lambda, and from lambda another one to say chi, and from chi to another state and so on. So, you actually depend, or rather generate a sequence of states, and these states are fairly independent from each other, because for a true Markov process as it is written here, the probability should satisfy that they should not vary with time. Okay. So, over the time these probabilities should remain constant, and they should only depend upon the properties of this pair of states mu and nu and no other states. Okay. So, this is very important, that for the probability in going from mu to nu will depend upon the properties of these mu and nu states and no other states that are there in the ensemble. And of course, the normalized probability should also be equal to 1, and this is true for any for all states nu, the final states, and this is a normalization of the probabilities. Okay. So, in a Monte Carlo simulation, one uses the Markov processes, these processes that repeatedly to generate a Markov chain of states. This is what exactly I was saying, that starting with a mu, we use the process to generate a new state nu, and then use nu to generate another state lambda, and then proceed in this particular manner to generate a large number of Markov states. So, the Markov process is chosen specially when it runs I mean when it runs for a long enough time, starting from a given initial state, it would eventually produce a succession of states which appear with the probabilities given by the Boltzmann distribution. Okay. So, reaching the Boltzmann distribution is equivalent to coming in thermal equilibrium for a particular case. So, as you generate more and more Markov chains, or rather states in the Markov chain, what happens is that you are likely to reach an equilibrium which is called as the thermal equilibrium, or is called as the Boltzmann distribution. And so, what happens is that what is the particular utility of this Markov process? Without the Markov process, we would have chosen states with at random with probabilities which are given by or proportional to exponential minus beta ei, ei being the energy of that particular state or that configuration. And this actually would have been more disastrous compared to our even simple minded Monte Carlo, and we would have actually landed up rejecting virtually all states because the probabilities for their acceptance were exponentially small. Okay. So, just without the Markov process, if we have gone ahead and used this probability, we would have virtually left out all states, because any particular state would come with an exponential small probability, and that would have served no purpose. Okay. That would have been even worse than actually calculating the whole the Monte Carlo estimate with a uniform distribution. So, let us quickly go through the details of the simulation. So, we wish to start from a random configuration of spins in a L cross L cross L system, which is equal to n spins, and L being the the lateral dimension of the lattice. So, we have a simple cubic lattice consisting of L cube number of spins. So, for this one can generate a random number from 0 to 1 and multiply that by n, which is equal to L cube, and approximate it to the nearest integer to identify the spins in the on the lattice. So, okay. So, this is not there. All right. So, what we mean to say is that you want to identify sites in the lattice and that you want to do randomly. So, what you do is that you either so you identify a state by this method or a site by this method, rather it is a site in that lattice by this method, and then you occupy it by a either an upspin or a downspin. Okay. And to produce a Markov sequence, if you use another random number generator, so that a particular spin is picked up, say Si, and this call this configuration as configuration mu. Okay. So, you start with a random configuration of spins by generating a random number where spins are, you say that between 0 and 1, if it's less than 0.5, I'll put a down spin, and if it's greater than 0.5, I'll put an up spin and things like that. So, randomly in the lattice you have put up and down spins. Then you need to generate a Markov sequence, your generator. Okay. And for that you pick another random number, okay, use another random number generator, and call that identify a spin by that random number generator by multiplying it by n and approximating to the nearest integer. Call this particular configuration as mu, at mu means the initial configuration. Now, flip the spin from, if the spin is initially up, then flip it to down, or if it is initially down, then flip it to up, and call this new configuration as new. Okay. So, you have an old configuration mu, which has from a given random distribution of spins on lattice, you have generated that. Now, you have identified one spin and have caused a flip, call this new one as new, the new state as or configuration as new. Calculate the change in energy according to the Hamiltonian. So, Hamiltonian is just writing down the Ising term, it is Si Sj with the Ij. So, you calculate the energy of the, or the change in energy of the Hamiltonian E mu and E nu, E mu minus E nu. So, let us call that E mu nu as E mu minus E nu, and so this difference is defined as this, and now this E mu nu will decide whether the move is acceptable or not acceptable. Okay. So, this flipping of spin is acceptable or not, and so we define certain conditions that if E mu nu is negative, that is the because of this flip the energy is minimized, then we accept the move immediately without any further condition. Now, even if E mu nu is positive, we draw another random number x and check whether E exponential minus beta E mu nu is greater than x, then if you accept the move, and if it is less than so this should be less than instead of this. So, we will so this is not, if you have a greater than equal to, then of course you accept the move, if it is less than, then you reject the move. Okay. You can't have both greater than equal to and less than equal to. Now, repeat this procedure several times by forming a long trajectory in the configuration space. So, what I mean to say is that you identify another spin, do the same procedure and see that accept the move or reject the move, go to another spin, and you again pick up a random number, identify a spin, flip it, see whether the move is acceptable according to this condition and things like that. So, we actually generate a long trajectory of these system in the configuration space, and this is precisely called as the Metropolis algorithm. There are more things which are ergodicity and so on. I will not go into details, but what our motive is to explain that these Monte Carlo simulations are particularly very important for a variety of situations, including a simple computation of simple integrals to very complicated cases such as this, see phase transition and things like that. So, this is roughly the simulation details. The expected value of the magnetization is computed so as to demonstrate the phenomena of phase transition. So, after the thermalization, after the the system has achieved the equilibrium or the Boltzmann distribution, the thermal equilibrium, so to say, then you calculate the magnetization and see that if the magnetization has a finite value and large value, so to say, so that we can say that the system is magnetic. And if it is either 0 or very small, then we will have to say that it is a non-magnetic system or poorly magnetic system and so on. So, if you have a varying parameter, say temperature, or that J over kT, then there is a particular Tc that one can achieve. Tc is the transition temperature. So, one can identify a transition temperature in a given system, and this is from a paramagnet to ferromagnet. This transition temperature is called as a Curie temperature. Incidentally, in one dimension, the system has no transition, that is the transitions are only at t equal to 0, which means that there is no ordering temperature, finite ordering temperature. And the reason is simple. The reason is that the energy difference between the demagnetized states or the paramagnetic states and the magnetic states is only by just breaking one bond, and that is a 1 over n effect. So, if n is large, that effect is very small, and then you always have a disordered system or a paramagnetic system excepting at t equal to 0, which is not a physical reality. Okay. So, these are precisely where they are applied. Let me show you an algorithm which will make things a little more clear. So, it is a flow chart for Monte Carlo. So, we will have so this, I am just drawing the boxes and then we will write what are the steps and things like that. So, this and okay. And then there are just give me a minute to finish this drawing. So, set up an initial configuration to define H, and you can set a counter here. Okay. Then you come to this one and then you say that flip a spin and calculate delta E, which is delta E equal to E mu minus E nu. If delta E is less than equal to 0, then you accept flip, which we have said. If delta E is greater than 0, then choose rand, so random number x. Okay. Then you see that whether uh, whether x um, x is uh, greater than equal to exponential minus beta delta E. If that is the case, then you accept the move, accept flip. If not, reject the flip, and one actually goes to a new configuration. So, then you calculate uh, q, which is equal to, you know, sum over all these states, and then q n or q I, whatever we have written earlier, q I and exponential minus beta E I divided by exponential minus beta E I, and so on, and stop iterations when delta E becomes almost equal to 0, which means that the system is not iterating and the system has reached an equilibrium, and then by flipping farther spins the energy of the system is not changing. So, that is the equilibrium that we are talking about, that is the thermal equilibrium that we are talking about, and then of course, use this Q, which is equal to 1 over m sum over Q I from 1 to m, and then use this thing to calculate the expectation value of the quantity that you are interested in. As we have told several times that this could be the magnetization, and the magnetization being non-zero would indicate that the system has gone into a ferromagnetic state. Okay. And one can do this in one dimension, and one does not find any phase transition, which means that there is no finite temperature at which or rather this J by kT is not you know at any. So, this only happens at t equal to 0, which means the value of this ratio to be infinity, but in 2 and 3 dimensions there are finite temperatures at which the phase transition occurs. Okay. So, we have seen very elaborately the utility and the versatile nature of this Monte Carlo simulation, and these are a very important you know simulation tools that are accepted by the computational community, both in you know various branches of science and engineering. The good thing is that you know a lot of things one does not really need to know, and it depends upon some distribution which is more preferred than other distribution. So, these are important sampling. The important sampling is a very important step in improving the accuracy of this Monte Carlo method. We shall stop here and with this discussion on the Monte Carlo, and will proceed with another simulation in the next discussion.